a non-commutative generalization proposed by Huang in 2012. And actually, let me actually start with the outline. So first, I will explain the axioms for the meromorphic open string vertex algebras and its modules. Then I will give the universal Bosonic construction, fermionic construction. So these are actually universal constructions for MOSFETs, and those are the earliest examples as well. And then another interesting example is just the Bosonic construction on Riemannian manifolds. So then this will basically be 3 examples I will discuss in the talk. And then I will discuss some future work and future projects that's possible. Okay, so let me first explain what is a meromorphic open string vertex algebra. So the motivation is to use vertex algebraic methods to describe the 2-dimensional nonlinear sigma model. So the idea is actually, so first, we want to realize certain differential operators on a Riemannian manifold as components of some vertex operators. So in order to do that, so the vertex operators cannot be commutative. So unless the manifold is flat. So this is the motivation to go into the world of non-commutativity. On the other hand, we will still need associativity because, well, this is motivated by the quantum field theory. So because we always want operator product expansion, and associativity gives us the OPE. Okay, so therefore, it is natural to consider algebra structures of vertex operators satisfying the following. So for U1, U2, V, and V prime, so the products, so the matrix coefficient of the products of 2 vertex operators and the matrix coefficient of the iterate of 2 vertex operators, they have to converge absolutely in these regions. And moreover, they have to converge to a common rational function with the only possible poles at Z1 equals to 0, Z2 equals to, and Z1 equals to Z2. So the notice, well, if you switch the 2 vertex operators, so namely you put U2 in the front and U1 in the back, so this guy still converges absolutely, but then it's not necessarily to the same rational function. Okay, now let me explain the axioms. So a meromorphic open string vertex algebra is first we require a Z-graded vector space, and the grading is just graded by weights. So it will be, and then we will need the vertex operator map, sending U tensor V to Y of UX V. And we also need the vacuum. And then the axioms are going to be the following. So first, we need to have an axiom for the grading. So we need to have a lower bound condition. So basically when n is sufficiently negative, so this guy, the Vn equals to 0s. So this n over here has a lower bound. The second condition we require is the lower D bracket formula. So here the lower D is simply the grading operator. So then we require the grading operator lower D to satisfy this lower D commutator formula. So basically speaking, this is playing the role as the L0 operator. Okay, so the next set of axioms is for the vacuums. So we require identity property and creation property as usual. So I won't go over this in detail. Then the next requirement is the capital D derivative and capital D bracket properties. So the capital D is defined in formula to be this guy. So in components, it simply says dV equals to V minus 2 of 1. So this is the same as the traditional definition for the capital D. So then we basically require that this is basically the D derivative property, and this is the D bracket property. So basically the capital D is playing the role as the L-1 operator. So we require L0 and L-1, but we are not requiring others. Okay, so these are the first three conditions. The next condition, well, Huang will call it rationality, Igor Frankl will probably call it duality. So but this is also quite standard, but there's a little bit difference in this context. So we start with the graded deal of the V. So instead of requiring the duality or rationality of product of two vertex operators, now we require the rationality of product of n vertex operators. So basically for any natural number n, and u1 through un and v prime, the matrix coefficient of the product of the n vertex operators, they have to converge in the region when the absolute value z1 greater than etc. greater than absolute value zn greater than 0. And moreover, we require the limit to be a rational function in z1 to zn, and the poles are restricted to be zi equals to 0 and zi equals to zj. So that's the rationality of products of n vertex operators. So this is the product. Once we assume the rationality of product of n vertex operators, when we come to the iterate, it turns out that for the iterate, we only need to assume it for two vertex operators. So then basically the matrix coefficient for the iterate will converge in this familiar region and to a rational function with the familiar poles. So that's the requirement of rationality. Okay, so this is the fourth set of axiom. And final set of axiom is associativity. So basically the product and the iterate of the two vertex operators, they should coincide in their common region of convergence. So basically speaking, the rational function of the left-hand side should coincide with the rational function of the right-hand side. So that will be the axioms for the meromorphic open string vertex algebras. So you could see that we skipped commutativity. So one remark is we require n vertex operators is because there's no commutativity. When there's no commutativity, starting from two vertex operators, you cannot prove the rationality that easily. So you need to assume the convergence of this guy, because that has to be proved with actual conditions. Okay, so these are the axioms for the algebra. So I will not go over the axioms for the left modules, right modules, and bimodules. Well, I just discussed this. Philosophy is the same. So all defining properties of the algebra that make sense, well, these properties should all hold. So this is how you define left modules. For the right modules, we basically require that all the properties of intertwining operators of this type that make sense should hold. So this will lead to the definition of right modules. I will not include it actually here because it's very long. So for bimodules, it will be defined as a space with a left module and a right module structure. And we require them to be compatible with each other. So that's, yeah, these are all in my JMP paper published in 2019. So I will not go over them. So let's actually start discussing the examples instead. So the following universal bosonic construction is actually given by Huang himself when he was defining the meromorphic open string vertex algebra. So we will start from the German age. Yes, please.
So for the modules, you still don't have any monodromy, right? So you still have integral powers of z?
Yes, that's right. For modules, we still have integral powers of z. Yes, there's no monodromy involved on the level of modules, but on twisted modules, as I will discuss a little bit later, then there will be a 1/2 power, so there will be monodromy. Okay, so that will appear in the universal fermionic construction. Okay, we start with finite dimensional Euclidean space over R. So this is my German H. Then I will just construct its affinization. So this is just the standard way of affinization. Moreover, so we could notice that there's for the affinization, there is this familiar triangular decomposition. So here, HC, this simply means the complexified vector space C, because we assume H to be over R. So, but then everything has to be extended to complex field. All right, so that's my H and H hat. So now we will consider N of H hat to be the quotient of the tensor algebra T of H hat. So notice that here, for usual Heisenberg algebra construction, so it's basically the quotient of the symmetric algebra, but now we are not using the symmetric algebra, we are using the tensor algebra. So N of H hat will be the quotient of the tensor algebra modulo the following two-sided ideal generated by these elements. So these are actually very long, but I have to explain one point. So first, in the first set of relation, so you see that this is very similar to the Heisenberg relation, but then something is missing for our definition because we require that M has to be positive and my N has to be negative. So basically speaking, this is saying that we are not requiring any relations between x tensor Tm and y tensor Tn when Mn is both positive, when Mn is both negative, and when Mn equals to are both 0. So these guys, we are not requiring any relation to them. So they are simply free. So simply so the second part, we are only requiring the P to be non-zero. So when P equals to 0, again, there's no relation. And for the last one, well, the central element is supposed to be commutative with everything. So that part we will keep. So you see that we are actually quotienting much less than the usual Heisenberg VOA. So that's the algebra N of H hat. So nevertheless, we still have a PBW type theorem. So that N of H hat is isomorphic to the T of H hat minus tensor T of HC, tensor T of H hat plus tensor T CK. So this isomorphic is as vector space A. So it's a linear isomorphism. Okay, so now let's see what we do the next. So we will just consider the one-dimensional vector space C. We will actually indulge a module structure. So we let H act trivially. We let the central element act as a scalar L, and we will require all the positive mode acts by 0. So this way we get a one-dimensional module for the algebra N of H plus direct sum with H0 hat. And then the induced module, so would then be isomorphic to T H hat minus as a vector space. So this is just, again, this is a very standard procedure of forming the induced vertex algebra, actually. So if we denote the action of H tensor Tk by H parenthesis K, then similarly as what we have seen in the Heisenberg vertex algebra, so we also have Th hat minus to be spanned by element of this form. So the only thing is actually here, this K1 can Kn, so they are not required to be admitting an ordering. So you don't expect to actually parameterize things by partitions. So that's so this is the spanning set. Moreover, to define the vertex operators, we need the normal ordering. So the normal ordering is defined as following. So the normal ordering of this set of operators is going to be the permutation of these operators. Well, but now the permutation is uniquely determined by the following set of conditions. So first, the guys sitting in the front has to be of negative modes. So negative modes in the first, 0 modes in the middle, and finally positive modes are pushed to the back. So this is actually still similar to what we have seen in Heisenberg VOA, but the actual thing we have over here is the ordering. So for example, in this case, we have got H1 of 2, H2 of 1, H3 of -1. If we take the normal ordering for this guy, so it will be H3 minus 1 will be pushed in the front, but H1 of 2 and H1 of 1, or H2 of 1 will be pushed in the back. So the warning is actually you are not supposed to interchange these guys freely, because so this is basically the requirement for this ordering. So the ordering of this Q1 shall be kept in the final normal order expression, and then you do not have the liberty to interchange them. Okay, so that's the explanation of the normal ordering. So then using this, so then Huang basically proved in 2012 that so viewed as a left NH hat module, so this TH hat minus, it will form a gradient restricted mass bar with the following vertex operator. So the vertex operator is defined completely the same way as the Heisenberg vertex operator. So you just take the appropriate derivatives of the H1, HIX, where HIX is simply going to be the generating function for all the operators HIN. So then you put all the appropriate derivatives together and you take the normal ordering, and that will be our vertex operator. So this is actually the universal bosonic construction given by Huang in 2012. Okay, so this is the bosonic version, and as you would expect, there should be a fermionic version. So the fermionic version is basically the first example of non-commutative vertex superalgebras and Z2 twisted modules. So the features are going to be following. So the algebra is graded by half integers, and correlation functions are usual rational functions. So there's no monodromy in the algebra part. On the other hand, on the modules, so when we talk about the Z2 twisted modules, so the module is still graded by integers, but then the correlation functions will have to involve half integral powers. So in this case, you do have monodromy. So this example is basically the non-commutative generalization of the Feingold-Frankel-Ries construction. So although the computation is much more horrible than there. So this is basically the joint work with Francesco Feudalisi, and I believe Shashank certainly knows him very well. So before he graduated, he already come to the algebra part, but the module part, he didn't come to the module part. So that's why Huang did not want him to publish the results. So I have to finish the module part. And actually, yeah, the computation is much worse than the algebra part. Okay, let's go over the results. But then, well, conceptually, it's quite easy. It's just much more technical. So we still start from the finite dimensional Euclidean space over R, but now we will consider the following space. So H hat Z plus 1/2. This is going to be H tensor R of the, well, plural polynomials, but with half integer power. So only 1/3, 1/2, 1/3. So these guys are actually going to be involved in the powers. So for this guy, you could also have a triangular decomposition, but there's simply notice that there's no zero mode here because there's the power is never going to hit 0. Okay, so we will similarly formulate the N space, which is the quotient of the tensor algebra modulo the two-sided ideal generated by the following element. So situation is very similar to what we have seen above. So we have only this M and N over here. We have M has to be strictly positive, N has to be strictly negative. And also notice that instead of minus in the bosonic construction, we are actually having a plus sign over here. So basically, this is the Clifford relation. So we have got the Clifford relation between positive and negative modes, but nothing else. So in particular, no relations for positive M and N and for negative M and N. So that's the space N of H hat. Well, similarly, NH hat, Z plus 1/2, this has got a, this satisfies the PW type theorem. So as vector spaces is isomorphic to these tensors. And we similarly start from the one-dimensional vector space. Let K act as the scalar, let positive modes act by 0, and we form the induced module, and the induced module is isomorphic to TH hat minus Z plus 1/2 as a vector space. So denote an action by R of H times O times T to the K plus 1/2 by H of K plus 1/2. So then you can see that still similarly, so the TH hat minus is spanned by these guys. Regarding the normal ordering, it's still going to be similarly defined. So you push all the negative modes to the front and all the positive modes to the back. So the only difference is that over here you have to involve a signature of the sigma. So that's the but that's the nature of the Clifford relation. Okay, then with this in mind, Francesco has already proved in 2016, although he's only showed computations, but basically he have already proved that this TH hat minus, so they form a gradient restricted meromorphic open string vertex. I will probably call it, we haven't decided what to call it yet, because it's actually the non-commutative generalization of superalgebra, but in my opinion, it's probably more appropriately to be called 1/2 graded meromorphic open string vertex algebras. So that's probably a more appropriate way to call it, but we haven't finished writing everything down yet. So just computations now. So we will think about the terminology a little bit later. So, and the vertex operators define completely analogous to what we have done before. So the only difference lies here. So here the HI of X, so first is going to be given by this half integer modes. But notice that the powers of this C series are still going to be integral powers. So that's the construction of the superalgebra. Okay, so that's the first part, namely the algebra part. So let me actually come to the module part. So the construction for module part just needs to start with the Z-graded space. So again, we start from the finite dimensional Euclidean space, and then we let H hat Z just the same way as the original H hat, but then we get a Z over here to denote some difference. So again, we have the triangular decomposition, and now when we form the NH hat Z, so it will still be the quotient of the tensor algebra HZ, THZ, but then the ideal is going to be slightly different to the Bosonic construction in the way, first, it's plus over here, so it's anti-commutators to be quotient out. And then moreover, overly positive modes and negative modes will have relations. And so it's basically the same comment. So it's no Clifford relations between positive modes, between negative modes, and between zero modes. So over here, so this is basically the anti-commutator of any non-zero modes with the zero modes. So this part still have relation, but no relations between positive modes, between negative modes and zero modes. Okay. So similarly, you have the PBW type theorem. So then NH hat Z is going to be isomorphic to this tensor as vector spaces. So in order to construct the modules, so we better start from H module by itself. So this is M. So starting with the H module M, so we let K act by a scalar. We let the positive modes act by 0. So then similarly, we form the induced module, and as a vector space, it will be isomorphic to the tensor of TH hat Z minus tensor M as a vector space. So similarly, we define the action, denote the action of the H tensor T to the K by H of K. So then we similarly have got a basic structure for this space. So the only difference is now actually the W can be ranging over N. So this is the first difference. And the second difference lies on the normal ordering. So the normal ordering in this case is much more complicated. So first it will still be a permutation of stuffs like this, but then where the permutation is determined in a similar way as before. So we want the negative modes in the front, the 0 modes in the middle. But then notice that, well, the 0 modes has to be going over a normal ordering procedure. And finally, positive modes at the rear. I think over here there's a typo. This should be strictly positive. So this should be strictly positive. Okay, so and another difference is the signature sigma in the front. And finally, let me explain the normal ordering in the between. So this is just determined. So the normal ordering of 0 modes are determined recursively by the following relations, actually. So this is, so for example, you can check that A1 of 0, A2 of 0, if you take the normal ordering. So this is going to be A1 0, A2 0, minus 1/2 of the inner product of A1, A2. So that's the example of the when R equals to 2. Okay, so this normal ordering is the familiar fermionic normal ordering in physics. So we are still keeping a lot of interesting features in this construction. All right, the vertex operators, on the other hand, is also going to be much more complicated. So we first define our naive vertex operators with the same way as before. So notice that here, so the vertex operators is given for associated to elements in the vertex superalgebra TH hat. So this is actually in T of H hat Z plus 1/2 minus. So for elements in the superalgebra, we have defined, discussed before. So we will assign the naive vertex operator with this form. So it's the same type of formula, but the difference now is the following. So the hi of x is the generating function of hi of n, but then the powers are not going to be integral anymore. So there will be 1/2 power involved in the procedure. Okay, so this is the definition of the naive vertex operator. So this vertex operator will not satisfy the axioms, and this vertex operator has to be corrected by a delta x. So let EI be an orthonormal basis of H, and we will construct the delta of x to be of this form. So first we need to, okay, so this is another typo over here. I think this should be EI, and this should be EI over here. So we can construct the following quadratic operator, and then times with the CNN, and then you organize them all together with the power x minus n minus n minus 1, and the CNN is determined by this formula. Okay, so this is the definition for the delta x. And using this delta x, we can come up with the actual vertex operator. So this is basically what we proved, I think, last November. So the left NH has Z module. So this will form a Z2 twisted module for the meromorphic open strings vertex superalgebra. TH had Z plus 1/2 minus via the vertex operator. So the vertex operator now is going to be, we first use the naive vertex operator, but then we have to correct the elements inside here by the exponential of delta x. So that way, that is the correct vertex algebra operator we should use in this fermionic construction. Okay, and here hi of x just was defined in the way we just mentioned in the previous part. Okay, I think sorry, I think I should really skip this actually. Yes, so this is not necessary. Yeah. Okay, so that will be the universal fermionic construction. Okay, so but then we have, so this is proved quite recently, and I think, yeah, I basically spent the whole last November struggling with all kinds of sign errors involved in the computation, and the computation is actually quite horrible. And the main problem is actually, so the computations used in Feingold-Frankel reads, those computations using exponential generating functions, those computation fails for the non-commutative settings. So basically this has to be proved using a different approach. And the approach I take is can be considered to be pretty straightforward as well as stupid and technical. So it's actually a huge computation to actually track this, but I'm glad that finally everything works out. But then to organize these guys into a reasonably long paper is actually a bigger challenge for now. Okay, but now we have got universal constructions, but is it going to be brainless generalizations, or is it going to mean something useful? Well, at least we could see, one can say the following. The Bosonic construction is already having some very interesting examples, and as I shall show in the next few slides. So let me actually discuss the Bosonic construction on the Riemannian manifolds. I actually have talked about this in the JMM conference last year, but then after that I detected a mistake in the paper, so then I should use the chance to make a few corrections and also report some new features actually. So, okay, so we start with a Riemannian manifold. We start with a Riemannian manifold and we fix a point on the manifold. So then we can take the German H simply to be the tangent space. So then the tangent space will then be a Euclidean space. And then then we certainly know that we have got a Mossbach structure on this tensor algebra of the affinized tangent space. So this is basically all follows from Huang's result. But this Mossbach does not contain any geometry information. And to incorporate geometry information, we will have to introduce the following. So first we will let Tm to be the tangent bundle, and we let the Tm hat to be the affinization of the tangent bundle. So here in this guys over here, so this M tensors M times the space of Laurent polynomial, so this regarded as trivial bundles. So similarly, this guy is also regarded as a trivial bundle. So then that way, so we have got a well-defined bundle, and we can actually consider the tensor of the bundle. So basically, it's tensoring the tangent bundle with the trivial bundle, then direct sum with another trivial bundle. So that's the geometry we are using here. Actually, we could probably try all kinds of different other bundles, but I haven't started yet. So this is, but that might also be an interesting thing to investigate. Okay, so we have got this affinized tangent bundle, and then we will get something much more horrible. So we will actually consider the tensor algebra of the affinized tangent bundle. So this is basically you tensor the TM hat with itself for arbitrary times, and then you direct sum all together. So this is still going to be a bundle. So I will just call it the tensor algebra bundle of the TM hat. Okay, so the geometry will come in the next step. So we will consider the following space of sections, and we will consider only the parallel sections of this big tensor algebra bundle. Okay, so it's well known in geometry that the space of parallel sections can be identified with a subspace of the fiber of this bundle. So the subspace is basically going to be the following. So it will be, you first consider the fiber, oops, something is wrong. And
for some reason, we can't see your screen anymore. I'm not sure what happened.
Yeah, so I think I saw that. So let me actually try to screen share again and share it again. Okay, so yeah, I feel like the screen recording software I'm using is actually not working very well. So let me see. Yeah, sorry for this.
It's okay. Worst case, you can send it to me and I can share it while you talk.
Because I need to actually get some annotations over here, so then that's why I probably need to keep it on my iPad. Let me please hold for a few more seconds. Okay.
Oh yeah, no problem.
It's now on.
Perfect. We can see it.
Yes. Okay, so it's pretty well known in geometry that this parallel sections, the space of parallel sections, can be identified with the fixed point subspace of the fiber of the tensor algebra bundle with respect to the holonomic group action. So it's going to be a subspace of something. And we already know that on this space, there is a meromorphic open string vertex algebra structure. So then this is basically what Huang proved. Actually, Huang proved actually something much better, actually. So for any open set, I believe, yeah, actually it's any open set will be good. So then on this space of parallel sections over this tensor algebra bundle, so the tensor algebra bundle of the negative parts of the affinized tangent space, affinized tangent bundle, so there is a natural structure of meromorphic open string vertex algebras. Moreover, but then this is actually still a formal construction. What is really interesting is the modules. So actually the space of parallel tensors, so they will act naturally on the space of the smooth functions. So the action is defined using covariant derivatives. So in other words, for a tensor of degree R, so we can actually define its action on a smooth function simply by this covariant derivatives. So we just take the covariant derivative of f. Oh, I think there's another typo over here. So this should really be R actually. So then, we just, for the tensor R, actually, we just take the rth degree covariant derivative of f along x. So this guy is still going to be a smooth function over U. So that's the, so this is the action of the parallel tensors on F. In general, this action is not very well performed, but then Huang actually showed if you restrict to parallel tensors, so then the action of X tensor Y is precisely the same as the composition of the actions of X and Y. So that basically tells me that this space of smooth functions will then form a representation for this algebra, where the algebra is actually defined using the tensors actually. So that's the first result by Huang. And the second result, so based on this result, so using the same induced modules procedure as you have seen before, we can actually see that the space of smooth functions over U, it will actually generate a natural module for the MOSFET, or that's going to be given by the parallel sections. And this module is induced from this action psi of U. Okay, so I said it's generated, so basically means the module is going to be much larger than the space of smooth functions actually. So it's not going to be this on the same space, but actually it's going to be giving you a lot of different stuffs. Okay, so then Huang actually asked the question, so can we determine the submodule generated by the eigenfunctions for the Laplace Beltrami operator? I will just use delta to describe it. So why do we care about this? Because such kind of module can be interpreted as the string theoretical excitation of quantum mechanical states. So quantum mechanical states are given by these eigenfunctions. Then we let this meromorphic open string vertex algebra to act on it. It will generate a lot of extra states, and those extra states can be understood as the string theoretical excitation in physics. So that's basically what he asked, and that's why I have been working on this. So in order to construct such modules, so it's necessary to understand the covariant derivative first. And then, so here is actually the result at least when I find this result, it was a very big surprise for me. So I will just restrict myself to restrict our attention to the Riemannian manifold. So we require it to be connected, we require it to be complete, and we require the Riemannian manifold to have constant sectional curvature. And moreover, we require the sectional curvature to be non-zero. Okay, so with this requirement over here, then for any connected open subset U, so we will actually consider a smooth function that's basically an eigenfunction of the Laplace operator delta. So then what happens is the following. So for any tensor of the parallel tensor of degree R, so the covariant derivative of f along x, this is a scalar multiple of f. So this is actually very strange in the following sense. So if you consider the space of parallel tensors, there are actually infinitely many of them. Actually, there is an infinite dimensional space. So you would naturally expect that the infinitely many tensors acting on a function f will give you infinitely many functions. It turns out not to be the case. You're actually getting one function actually. So you're not going to get any more functions more than the scalar multiple of it. So this is actually, so originally we were expecting an infinite dimensional representation. Well, we ended up with a one-dimensional representation. So this is, I still don't have any good conceptual understanding towards this. So it's just very strange. So it's definitely very much dependent on our assumption of constant sectional curvature. And actually I have a conjecture that you're only getting one-dimensional representations only exist when the sectional curvature is constant. So for more general cases, I don't think it's probably, we are going to get one-dimensional representation. Okay, so this is the result I have proved, and this is independent of dimension. Moreover, I can actually show that the scalar is actually polynomial functions of the eigenvalue. And when the dimension m equals to 2, so these polynomials can be fully determined. But when the dimension n is strictly greater than 2, it turns out that we do not know enough about these polynomials. I think Andy here is an expert on invariant theory, so he probably understand why this is the case. All right. Okay, let me continue. So once we understand this covariant derivatives, so then we can actually proceed to construct the Meromorphic open string vertex algebras and modules. So because we already have full understanding for dimension 2, so for the rest of the parts, I will restrict myself to two-dimensional Riemannian manifolds. We will restrict ourselves to complete, and connected. And also we require the Riemannian manifold to be oriented as well, because in this case, invariant theory is quite easy. I think it's not a very big trouble to generalize these two non-orientable manifolds, but then I was planning to actually incorporate the results into a paper of higher dimensional manifolds of constant sectional curvature, but there is actually a big gap in the arguments over there. So it turns out that we have to know enough about these polynomials to handle the higher dimensional case. Okay, now let me report what I have done. So let f be a smooth function that's an eigenfunction for the Laplace Beltrami operator. So we have computed the following. So first, the Meromorphic open string vertex algebra. I think this is again a typo. It's Mosfa. The Mosfa has been fully determined, and the module generated by the eigenfunction has also been uniquely determined. And moreover, one interesting feature is actually this modules admits a unique maximal submodule. So this basically makes it possible for us to determine the unique irreducible quotient. So we also determine the unique irreducible quotient of the module generated by the eigenfunction. So basically that's, so Huang's paper ended with this as a construction, but then once you pass to the irreducible quotient, some surprising things happen. So surprisingly, in the irreducible quotient, so we started without any relations about the annihilation operators and the creation operator, but it turns out that in this irreducible quotient, these guys automatically commute. So I don't know why actually. So this is the case. But then still, there's still some non-commutativity kept, namely the zero modes. So they do not commute. But the zero modes, they still satisfy a technical covariant derivative condition. So this technical condition will be able to fully describe the commutators. So basically speaking, we know they don't commute. We can compute all the commutators explicitly. So so these are the features. And more surprisingly, there are the following. So there's more surprise still ahead. So more surprisingly, so the irreducible modules generated by functions with specific eigenvalues, lambda equals to p times p minus 1k, p in z plus. So these guys are significantly different to those irreducible modules generated by functions with generic eigenvalues. By generic eigenvalue, I simply mean eigenvalue that are not of the form. So in case you're familiar with the spherical harmonics, so these are precisely the eigenvalues of spherical harmonics. So it turns out that these eigenvalues leads to very, very different irreducible quotients. So that's this is another thing I don't have any conceptual understanding. It just turns out to be that way. So, okay, so apart from this difference, there's actually something more interesting in terms of representation theory. So indeed, we actually classified all the lowest weight modules. So the lowest modules satisfying the covariant derivative condition. I didn't talk about it because it's way too technical. And moreover, we also require this module to have a finite composition series. And we actually found that if all the composition factors of W are generated by eigenvalues with specific eigenvalues, so then such a module is completely reducible. So this is kind of like the integral weights versus the usual weights, generic weights in the algebras theory. So the module category generated by the integral weights are much better than the module category for the generic weight. For that, we basically observed this phenomenon under this context of meromorphic open string vertex algebras. Okay, so that's basically the results I want to report. So the last part slides is just some comments and potential future work. So the first thing probably we should work on is to have a conceptual understanding from geometry analysis. So, well, all these results we have obtained is just follows from technical algebra manipulations. But how to understand these results in geometry and analysis, I believe that this kind of strange things will have a better explanation than my technical algebra manipulations. So this is first question. The second question is the higher dimensional manifolds of constant curvature. I have computed a lot on this one, and it turns out that it's reasonable for us to conjecture that all this kind of interesting features hold. And in particular, the generic eigenvalues are just going to be, it's still going to be the higher dimensional spherical harmonics. So spherical harmonic eigenvalues are still going to be special in higher dimensional manifolds. But the main obstruction for us to get the proof lies on the covariant derivatives. So we don't understand enough about those polynomials I just described. So this is the second part of the thing. Well, another question. I think that's basically Huang kept asking me this question. So what are the intertwining operators between these irreducible modules? So at the least, we expect that intertwining operators between those irreducible modules with specific eigenvalues. So this should be easy to define. But then, because now the curvature is kind of like, the curvature is non-zero. So the usual way that works for lattice VOA, so this doesn't work really well because, well, lattice VOA, you could actually interpret it as the construction on the torus, which is of curvature 0. So in that case, you could actually make, for example, like those exponential, the two exponential of two particular fields, actually to construct intertwining operators. But then when the curvature is non-zero, so whether or not such kind of, what mechanism should be working, this is not predictable at this moment. But this is definitely an important question. So what are the intertwining operators between this irreducible module? And if you were a physicist, then you probably care much more about tensor categories because you need to understand how those kind of strings interact with each other. So that basically means it's necessary to consider the tensor categories. And as I said, so for modules generated by functions with special eigenvalues, so I believe this is possible, and there should be a beautiful theory lying ahead. So we should be, yeah, this is definitely something that's interesting to study. Okay, so this is just going deep, and in the widths. So we could also consider, for example, other Riemannian manifolds that are not necessarily of constant curvature. Well, the most natural example is the complex projective space. And well, at least when n equals to 2, so the covariant derivatives are relatively easy to study. But then again, this is actually a huge computation. And it's also kind of unpredictable how many dimensions are we going to get for the parallel tensors actually. So that's the question. Okay, so what we described above is just the application of the Bosonic construction. So Huang actually asked Francesco and me to work on the fermionic version because we expect to have got a fermionic construction on Hiller manifolds and spin manifolds. And as I joked last in JMN meeting, so we would really like to get the situation, get things sorted out on Hiller manifolds so that to make this abbreviation, so just to insert a K over here to make the Russian word for Moscow. Okay, so that's another thing we want to do. And another necessary question: aside from the construction we just described above, is there any other constructions of masses and modules? So those are all the possible things to work on. Okay, so I should turn